Hi again. So we've been talking about the normal form games, and we're going to talk a little bit more about them, still talking about situations where we are looking at pure strategy Nash equilibria. And what we want to talk about next is expanding beyond the 2x2 simple games that we've looked at. So the advantage of 2x2 games is obviously they're very simple to illustrate and fit on a slide. But more generally, in many examples and applications that we're interested in, there are going to be more actions available to players or more players looking involved in a game. So let's actually take a look at a very famous game that has been analyzed in different contexts and illustrates a few points. So this is named Keynes' Beauty Contest game. And it gets that name actually because Keynes in 1936 was talking about a situation where there was a set of British newspapers where people would play a game where they had to name the picture that they thought would be the most preferred face out of 100 photos that other people could also pick faces. So it was a game of trying to match what other people were doing in the society. So in particular, the way we'll think about this game and the way it's often looked at is that each player is going to guess an integer between 1 and 100. And in particular, they want to guess the integer that is closest to 2/3 of the average of all the guesses. Okay, so we look at the mean guess out of all the players, we take 2/3 of that, and whoever is closest to that wins the game, and the other players don't win. So the idea of what Keynes was discussing in terms of talking about this game was the idea that there's a society out there and players would like to be in advance of other players. So if you're investing, you'd like to sell or buy a stock before other players are doing it, depending on whether it's going up or down. So you want to say sell just before everyone else sells or buy before everyone else buys. So you're trying to guess what other people are going to do and then do something in advance of that. So here the idea is the mean is what you're trying to predict, and then you're trying to get 2/3 of that. Okay, so let's look at how we'd represent that in a normal form. So now we might have many players, and it could be thousands, it could be hundreds, maybe 10. But in any case, let's take our set of players to be at least 2, so more than 2 players. And the action set here is AI is equal to the set of integers between 1 and 100. So you can name anything, 1, 2, 3, etc., up to 100. And how does the payoff function look like? What does it look like? So if we think about the average of all the actions, so let's M of A be the average of all the actions, the named numbers, then what does a person get? Well, you end up winning. You get a payoff of 1 in a case where you end up having the distance between the announcement and 2/3 of the mean being less than that of any other player. You get 0 if there's somebody else, some other player who ends up having a closer announcement to 2/3 of the mean than you do. And there could be a case of ties in this game, so it's conceivable that the players are going to tie. And if there's k players, for instance, who all are closest to 2/3 of the mean, then each person will just get 1 over k. So let's split things equally in a case where there's a tie. So now we've got a game. We can't, we could put it in a giant matrix, but it would have 100 different players, or n different players, 100 actions for each player. So here we're not going to be able to put that on a slide, but this representation gives us the normal form, and now we can begin to reason about what the play in this game is going to look like. Okay, so let's think about solving for an equilibrium in this game. So first of all, we can begin to sort of go through some reasoning. And given that you want to guess 2/3 of the mean, the best reply of any player, so something that you can check and is fairly easy to see, is that the best reply of any given player is going to be below the mean of the other actions as long as people are announcing things above 1. Right? So if everyone else is announcing something above 1, or the mean of the other announcements is above 1, then I'd like to be below that. So if the mean was 2, 2/3 of 2 is 4/3. The best number to announce would be the numbers closest to 4/3. That would be 1. So if everyone else is announcing 50, if you look, at the average of 50, then what would I like to announce? I'd like to announce 2/3 of that, roughly 33. You have to factor my own announcement into the average, but basically people want to be below what the average is. So when you begin to look at a game where everybody wants to announce a number below average, what's that going to do? It's going to lead to an announcement of everybody announcing 1. So when you actually look at the Nash equilibrium of this game, there's a unique Nash equilibrium. There's only one equilibrium point in this game, and it's for everybody to announce 1. Okay, so that's sort of a striking conclusion, given that we have all these strategies and available, but in this case, everything pushes down to everybody announcing 1. We can actually take a look at a histogram. This is a histogram of how some students played in a game, in this game, in a class that I taught at Stanford. And here, what do we see? Well, indeed, you see most of the players announcing things fairly low. You do see, so there's some people, these things are binned, so it doesn't list every particular bid, but there were a bunch of people near 50. There are some people who actually bid above 50. And actually, you see people here, some people bidding close to 2/3 of 100. Not clear exactly what the logic is there, but if they think everybody else is going to bid 100, then you could bid 2/3 of that would be 67. If you think people are going to bid 50, well, if you think the average is going to be roughly 50, then you'd want to bid near 33, right? So you see a bunch of people bidding in that range. Well, now you can begin to think, well, maybe other people are going to think that way. Maybe they're going to bid 33. Then if I go somewhere 2/3 of that, then I end up down here. But if people are bidding that, then there's some people who bid down here. But basically everything moves downward depending on what you believe other players are going to do. In this particular game, what happened? What happened was that you saw the mean of 18.2, the median about 14. So in this case, the actual winner of the game was somebody who had bid 12. So the mean was 18.2, 2/3 of that was 12, and in this case, so you didn't see them actually playing the equilibrium. They played well below 50, but they played somewhere above 1, which is the predicted equilibrium. So in this kind of world, part of what we're seeing is a situation where what you do has to depend on your prediction of other players. So if everybody thought everybody was going to bid 1, that's going to work. This is not an equilibrium play because you're seeing a lot of people bidding things that are not best responses. So in this case, if you knew what this histogram was going to look like, you could pick an optimal bid and win the game. So the question is making correct predictions, and in a large society that becomes more complicated. So actually what we can look at now is suppose we play this game again. So this is the histogram from the second time that the students played after they'd seen the results from the first time. And once they'd seen those results, then they realized that people were bidding much lower than they had initially thought. So now we don't see anybody bidding above 22 as the highest bid. And we see many more of the bids very low. And in fact, you begin to see the mean here is much lower than the 18. It's down to 4.76. The winner in this case was 3. And if you keep running this, then eventually things converge towards the Nash equilibrium. And now indeed we're seeing a lot of people play very close to what the Nash equilibrium play is of 1. And things keep getting pushed there as we keep playing this game over and over again. So here's a sort of situation where you begin to see convergence to Nash equilibrium as players are learning in a population of how things are going. But this gives us an idea that Nash equilibrium can make predictions in games with many players, in games with many strategies, so it's not just something for 2x2 games.